Thanks for coming to the latest American Physical Society Topical Group on Climate Physics seminar series. Before we get started with today's speaker, I just wanted to share the website so that people are aware of the GPC. If you're not a member, if you're an APS member and you're not a member of GPC, I want to encourage you to sign up. This is our Engage website. We have a number of newsletters, very nice newsletters that are put together. And the seminar series link is right here. You can click on that, and you can see all of the two more talks listed for this spring. But today we have Raymond Pierrehumbert. We are very pleased to welcome him to talk about solar geoengineering. Before I get started with an introduction, just a few ground rules, so if you have a burning question during the talk, please put it in the chat, and we will alert Raymond if he hasn't seen it, and he can try to answer it. And then at the end, we're going to have kind of a more open question period so that people can just unmute themselves and ask questions directly. In the meantime, please keep yourself muted so that we don't have distractions. That nobody likes that. So we will try to be on top of that, muting people as well if needed, because we do expect quite a few people for today's talk. And so we'll go ahead and get started with my introduction. As I said, I'm pleased to have Raymond here today. So Raymond Pierrehumbert has served as the Haley Professor of Physics at the University of Oxford since 2015, where he established the Planetary Climate Dynamics Lab. Recently, he joined the Department of Earth, Atmospheric and Planetary Sciences at MIT, which is where he's at today, in 2026 as a professor of practice. And I think he splits his time between there at the moment. His work deals with the physics of climate of the Earth and other planets, ranging over the past 4 billion years to the next several billion years, and extending from the solar system out to newly discovered exoplanets. This includes questions of near-term interest, such as the nature and impact of climate disruption that will result from human-associated emissions of carbon, global warming, and extends to things such as the effect of agricultural practices on climate change. He earned his PhD in aeronautics and astronautics from MIT in 1980 and holds a BA in physics from Harvard. Before Oxford, Raymond held faculty positions at MIT, Princeton, and the University of Chicago. He is the author of the textbook Principles of Planetary Climate, which I highly recommend, and was a lead author of the Intergovernmental Panel on Climate Change Third Assessment Report. Among numerous distinctions, Raymond is a fellow of the American Academy of Arts and Sciences, the American Geophysical Union, and the Royal Society, where he was named a Chevalier d'Or de Palme Académique by the Republic of France. And a fun fact, Raymond likes folk music and plays the accordion. So maybe he'll get a question about that by the end of the talk. But so with no further ado, I'm going to ask Raymond to share his slides, and he can take it away.
Okay, let me see, here we go. Okay, and let me get into full screen. Okay, thank you very much for that very, very nice and flattering introduction. So most of my work these days is on exoplanets, which is not so stressful because we can think about planets at 2000 Kelvin and lava oceans. We don't have to live there. I don't have to care whether politicians pay any attention to things I'm saying. But of the various Earth things I've been involved in terms of public communication, this business of solar geoengineering, which I've been tracking for the last 20 years or so, is the most stressful. And but it's something that needs to be talked about. And so by way of prelude, I have some of my family comes from Iowa. And so in the family, there's one of our favorite stories is the story of Kate Shelley, who in 1881 had to crawl across a derelict bridge. In fact, the actual bridge was much more derelict than this picture from a children's book shows. Crawl across a derelict bridge in a rainstorm to flag down a passenger train which was barreling towards a washed out mainline bridge. And I'm not saying that I've ever done anything nearly as courageous as what Kate Shelley did, but my point of resonance with this is that ever since I first learned about solar geoengineering from Paul Crutzen back in my early days at Chicago, which is now more than 30 years ago, I could see this as a train wreck coming. It was a very distant train and not a very big one. But what is really alarming, and what will be one of the main themes of this talk, is just how this juggernaut has grown and is steaming towards what I think is a real impending train wreck. It's a very controversial subject. I see Dan is in the audience. I know we don't agree on how dangerous this is, but this is my opinion, and there's a lot to discuss about just what the situation is. Let's start from the basics. I mean, the basic physics has not really changed. And what I say about how the physics relates to the difficulties or the dangers solar geoengineering, they really haven't changed in the whole time I've been studying this system. Despite the money that's poured into research on this, all of the basic issues that were identified in our 10-year-old National Academy report that I was involved in as a co-author, they're all still there and they haven't gone away. Some things have been learned on the fringes, but the basics haven't gone away. But I want to talk more about the funding context and the governance context, but I will go over the physics aspects again. But just to start from the beginning, the temperature of a terrestrial planet, or mostly rocky planet like the Earth, is determined by radiation balance. This goes all the way back to Fourier in 1827. That the amount of solar energy absorbed by the planet has to be balanced by the rate at which infrared carries energy out. Infrared is the only thing that escapes a planet, and Fourier knew that. And so these two things have to come into balance, and the hotter the planet gets, the more infrared it emits. And so that's your basic stabilizing stabilizing feedback that keeps the planet from melting. So when you increase carbon dioxide, or indeed any other greenhouse gas, it reduces the rate at which the infrared escapes to space, which, if nothing else happens, will require the Earth to warm up in order to balance the energy budget again. But if you increase the reflection of solar energy by clouds or whatever, aerosols, that reduces the input. So the Earth would have to cool down. And this happens during volcanic eruptions. But solar energy and infrared cooling affect the climate in very different ways. And so you're not really putting the climate back into its original pre-industrial state. Solar energy, for example, in Earth's atmosphere is mostly absorbed at the surface, where it drives precipitation and diurnal cycles and things like that. And the solar energy is unevenly distributed around the globe, and in summer versus winter, whereas CO2 effects are more uniform and global. And CO2 radiation happens not just from near the surface, but high up in the atmosphere. So changing the CO2 affects the surface energy budget and the low-level cloud energy budget, which I'll get back to very briefly, in a very different way from solar energy. Now, simulations show that the atmosphere has a certain ability to even out some of these mismatches, but is very imperfect and subject to uncertainties in a whole lot of things that models are not very good at, like regional precipitation patterns. But so the basic cartoon. Can people see my cursor? Yeah. Okay. Yeah. So the basic cartoon is if you the albedo of the Earth, the reflectivity of the Earth, is determined by high clouds, by stratospheric aerosols like you get from sulfate volcanic eruptions, and also by low clouds and then things on the surface like ice and vegetation and so forth. Uh, Now, in the pre-industrial climate, before we start increasing CO2, you have a certain largish amount of radiation going to infrared radiation escaping the Earth, balanced by an equal amount of absorbed sunlight, which is the net of incident minus reflection. Now, when you increase a greenhouse gas like CO2, you shorten this infrared arrow if the climate stays the same, if the temperature doesn't warm. So that would normally throw things out of kilter because you then have less going out than is going in. What solar geoengineering tries to do is compensate for this arrow, which has one kind of physics, by changing the incoming arrow, by bringing the Earth into energy balance without the global mean warming up, by reflecting some sunlight back to space. Reflecting some sunlight back to space by changing the reflectivity. There are two different general schemes for changing the reflectivity. One is stratospheric aerosol injection, which is kind of a misnomer because not all the schemes inject aerosols themselves. So, the most widely thought about scheme injects sulfur dioxide or other sulfur compounds, which will chemically react and turn into aerosols and mix with water, which is part of the difficulty in knowing the albedo you achieve. And the other scheme is marine cloud brightening, which and both of these schemes have the same basic issues with regard to mismatch in timescales, which I will get to later. There are variations on the theme of engineering the Earth's energy balance. For example, there's a cirrus cloud thinning scheme, which attempts to actually affect the infrared by changing the properties of cirrus clouds. That seems very hazardous to me, because particularly hazardous because cirrus clouds are some of the least understood kinds of clouds in the climate system. If you do it wrong, you could actually make warming a lot worse. So, but anyway, so that's the scheme. Harvard SCOPEX experiment, which was not directly doing geoengineering, but doing some outdoor tests, proposing outdoor tests of dispersal of things released from balloons in the stratosphere and so forth. That was an example of an early proposal for outdoor field experiment, but it's not the only one anymore. I don't know if SCOPEX is even considered to be an active proposal anymore, but we'll see that the world is barreling towards actually doing outdoor field trials in the stratosphere, and is already doing outdoor experimentation in things that almost verge on deployment with marine cloud brightening off the Great Barrier Reef. And so the kinds of things that worry me most are not so much simulation. It's the great growth in the funding of things that are basically developing the engineering to actually make deployable technology without answering the fundamental questions of what would happen under a deployment. And that's really the focus of what I'm sounding the alarm on in terms of recent developments. But you put the Earth into a non-analog climate when you engineer the albedo, an example of what you're doing is you're putting the climate a little bit back into the kind of state it was in the Ordovician, when the sun was about 3.5% dimmer, 450 million years ago, and that was compensated by carbon dioxide that at some times in the Ordovician before the glaciation were maybe 4 times pre-industrial and so forth. So that's we could go to 4 times or even more if we continue burning fossil fuels. We're not going to run out of fossil fuels before you get there if we do continue without decarbonizing. And now there's a difference though, because that's not completely analogous. First of all, I mean, back then, we didn't have the kinds of, we didn't have humanity that needed to be fed. We didn't have all the range of mammals and ecosystems we have now. It was a very different world biologically. But the other difference with the Ordovician is that the sun was 3.5% dimmer because of main sequence stellar evolution. The star like the sun does not suddenly flare up and get 3.5% brighter. Whereas the essential risk, one of the biggest risks of solar geoengineering, which is the one I've been hammering on for 20 years, is that aerosols and an enhanced marine cloud albedo disappears in very short time periods. So, a week for marine cloud brightening, a year or two for stratospheric aerosols. So it's as if you have put the Earth in a situation around an M star where you could have a flare that suddenly increases the solar brightness by several percent. So, and so we don't know. It's hard to anticipate everything that would go on in those non-analog climates. But the new development, like I said, in terms of the basic physics, there's that's going on. Not much ground shaking has really happened, and I'll mention one area which definitely needs more research, but that's not the kind of research that is mostly happening. There is a whole flood of money. This is the thing that is really different. It's turned around dramatically in the last few years. There's just a whole flood of money pouring into solar geoengineering. And you might think that this is something that's funded nefariously by the fossil fuel companies, but mainly the fossil fuel companies are pitching carbon capture, air capture as a way of continuing burning fossil fuels. I think that's mostly a dodge to allow them to avoid facing the issues of decarbonization, but that's their main pitch. That's been the fossil fuel industry's main pitch. Most of the backing for solar geoengineering technology has come from an alliance of high-tech and financial tech industries. There's an NGO that exists solely to lobby for solar geoengineering, not just research, but actual deployment. In the previous Congress, they were fairly influential lobbying for federal funding. Now, the present Congress seems not to want to think about anything about climate, and I don't know what is happening I don't see anything going on in the U.S. funding structure from the federal government, but Silver Lining is largely funded by a collaboration of Silicon Valley companies. The Simons Foundation which is funded by Renaissance Capital, and Simons does funds absolutely amazing work on astrophysics and on neurophysiology. But they decided to dump about $10 million a year into doing research on solar geoengineering. So far, not covering outdoor experimentation, though they do cover some engineering development with that. And our Environmental Defense Fund, which is an environmental organization, which shows the sort of the turnaround and the perception that in a panic we have to do something. Environmental Defense has accepted what they say is millions from the LAD Climate Fund that's a forestry products company, I think, for solar geoengineering research. I wonder how their grassroots donors would actually feel about that if they knew about that direction. It's an interesting question. Then there's the Degrees Initiative, funded by Open Philanthropy, which is largely Facebook money, which has been funding a whole portfolio of solar geoengineering research largely in the developing world, which in some sense is good because it provides employment for researchers in places where funding is scarce. On the other hand, one of the inadvertent or who knows what results of the Degrees Initiative is that it has led to the creation of a number of advocates for vastly expanded solar geoengineering research and even deployment, some of whom have made their way into the IPCC apparatus and are backing more research there. In fact, IPCC in this round has a chapter on what's called Overshoot, which has a lot of well-known geoengineering, a certain number of geoengineering advocates on it. The Quadrature Climate Foundation is putting $40 million into geoengineering research at University of Exeter, Colorado, and Silver Lining is also putting money into research as well as lobbying. University of Chicago, which hired David Keith away from Harvard, has really gone big full time for geoengineering. They had given him 10 full-time faculty slots devoted to a center for climate intervention. It's not all solar geoengineering. It doesn't, strangely, involve carbon capture, which is a kind of geoengineering that would be wonderfully valuable if it ever became economic. But it's interesting, this was created without any real consultation with the Geophysical Sciences Department at Chicago. The incoming university president asked the economists what he should do in this climate area. And this is what they came up with as the big thing they should do in the climate space. I could think of lots better uses of 10 full-time faculty slots. Chicago is under some real financial pressure. I don't know how things are progressing towards filling these faculty slots. I know some of them have been filled, but it was really putting a lot, and it's indicative of the normalization of geoengineering, solar geoengineering research, which is entering major universities, and not just in the United States. In Cambridge, England. Cambridge, England has the most hubristically named center for geoengineering research I could possibly think of. They have this entity largely from the engineering department, not the earth science department there, the Center for Climate Repair. So NERC, which is the equivalent of it's the Earth Science Funding Council, has put 10 million pounds of geoengineering research funding, mostly for simulations from NERC, across 4 projects. And the fine print here, this is from an earlier press release from the Center for Climate Repair. The fine print here is that the NERC funding, that this is a field trial of one of their geoengineering, Arctic geoengineering deployments. The fine print here says field trials will not be funded by NERC. That's true. NERC is funding simulations, but ARIA, which I'll get to next, another UK funding agency, is funding field trials. In fact, is funding this exact field trial that you see there, which is an attempt to artificially thicken Arctic sea ice. So ARIA, what is ARIA? So ARIA is a DARPA clone that was come up in the by the previous government, and like DARPA. Its philosophy is to give pots of money, large pots of money on the order of 60 million pounds to individual directors that they hire. And then the directors can do whatever they want and decide what kind of peer review they want, if any, what kind of review and so forth. One of the directors, who is an electrochemist with no background in climate whatsoever, has put 58 million pounds into exploring a project called Exploring Climate Cooling. And what's alarming about ARIA is it's not a fundamental science agency. It is also not subject to the kind of rigorous peer review that things like NSF, at least in the good old days, and NERC are subject to. It's largely discretionary at the hands of the directors. Who in this case, this one is extremely inexperienced in climate. You can see that in the initial call for proposals. But ARIA is, as I said, not a fundamental science agency. It's a technology development agency. So it is exactly the wrong kind of agency to be handling funding in an area where we don't even know the answers to many of the fundamental scientific questions. But their mission is to actually develop deployable technology. And what's worse, it's lacking in transparency. One of the few things David Keith and I completely agree on is that if there is going to be research on solar geoengineering of any sort, it has to be subject to transparency. But ARIA, by its construction in the legislation that set it up, is not subject to freedom of information requests. So you can't even really know what they're doing and what their ground rules are, except what they choose to release themselves. And this is some of the things that they're funding. There's already, as I said, some small-scale deployment of attempts at marine cloud brightening over the Great Barrier Reef in Australia, but they're funding a greatly expanded deployment of marine cloud brightening. I should, as a side remark, there's sometimes this sense or description that marine cloud brightening is just a regional intervention. It's something you could surgically do in one place that doesn't have global repercussions. But in fact, to significantly cool down a patch of the ocean, you really need to deploy it over a big enough area that you're not overwhelmed by the surrounding warm water and warm air. Once you deploy it over a big enough area, the climate system is very interconnected, and you are going to have at least hemispheric repercussions of these sort of things. And other engineering things for marine cloud brightening, there are two projects that are developing aerosol dispersers for marine cloud brightening, including field tests as well as lab experiments. And these involve for-profit corporate partners, one of which is Archipelago Technologies. So the profit motive is entering explicitly. Patents are going to come out of this. I mentioned the sea ice thickening, which is being done in the Canadian Arctic. No, ARIA is funding things that are not even under the direct environmental controls and governance, whatever UK might actually impose. The sea ice thickening is being done in the Canadian Arctic in collaboration with for-profit partners, Real Ice and Arctic Reflections, which seek to make money off of this. And actually, this is a really ludicrous technology, the sea ice thickening. There are many peer-reviewed papers which show that this is completely pointless and expensive and a thing to try. So that's a waste of money. That's not going to actually do very much, but it could have adverse local effects. But there's another project that's engineering of particles for stratospheric aerosol injection that includes in situ balloon-borne experiments. But it doesn't actually release the particles, but it looks at how the particles age. So it's aimed at developing a new class of deployable particles. And they're even funding the engineering design of orbital sunshades. And lest you think that this is too crazy to even think of putting in orbit, given launch to orbit costs, there's actually a for-profit company called Reflect Orbital that has a pitch in to actually put a giant mirror in low Earth orbit. Now they're not pitching that for geoengineering. They're pitching it for providing sunlight at night. Actually the optics just don't really work out, but they're really on the verge of getting permission for launch. And that's actually quite a dangerous thing from the standpoint of low Earth orbit, because if a great deal of debris would be created by these reflectors as they eventually degrade and break up. So it's more junk for the low Earth. But you'd have to have thousands and thousands of these things, maybe millions, in order to have a significant effect on nighttime illumination. But it's essentially developing, but ARIA is actually funding or engineering development of orbital sunshades, which are not necessarily mirrors, but things that aim to divert sunlight. So, and now what's really alarming is that the profit motive is and startup venture capital is coming into this is coming into this suddenly in a really big way. The Israeli, well, they're registered partly in Maryland, but the company itself is essentially an Israeli company with graduates of the Israeli defense industry for the large part. The startup called Stardust has gotten just in their first funding tranche $70 million of venture capital funding to develop particles and deployment technology. And they actually have already done low-level outdoor release experiments with their proprietary particles. Nobody knows what these particles are. I suspect they're calcite, but everybody who's been given access to talk to them, including Janos Pastor, who was on their board for a short time before he realized that he was being used. Everybody who's visited what they're doing is under a non-disclosure agreement. So this is the epitome of non-transparency, and these people are not just there for research. They plan to make money by selling these engineered particles to deployers, and they're also working on deployment vehicles in the long run. Their website, completely over the top, describes this as a safe, measurable, adjustable, and fully reversible system to stabilize Earth's temperature, sloughing over all the subtleties and difficulties. And Politico did manage to get a hold of one of their venture capital slide deck pitches, where they actually have a timeline for deployment. They actually plan to make money by pushing actual deployment. And right now, in the absence of governance, this is, I think, about 2035. They're going for, a pretty big scale deployment, and the associated amount of money they would make by selling their patented particles. And there's no governance. There's absolutely not a blessed thing that can be done to regulate the scale or the nature of the deployment, who does it, and to what extent. And so this is I'm not against all kinds of research. We have learned some interesting things from simulation. You always have to take the simulations with a grain of salt. But that's the one way we have of knowing something about what would happen globally under a deployment without actually doing a full-scale deployment. But a huge amount of the new funding, maybe most of it, is for engineering that's in aid of deployment and not for addressing fundamental scientific questions about what happens if there is a full-scale deployment. And one of the problems with solar geoengineering, and I think maybe this is something Dan Schreig and I may even agree on based on the title of his talk about unknowable geoengineering that he's giving at Oxford in a couple of weeks' time. It is probably most of the big questions about effects of solar geoengineering are unanswerable with any kind of small-scale field trials. They would require not just global-scale deployment, but monitoring what's going on for a long period of time. If you want to see what's happening with El Nino, you've got to go through several El Nino cycles, and then there's natural variability. So engineering is the wrong question, because if we deploy it, we won't really know what we did to the climate for many years. And is it really wise to do so much engineering research that will make deployment technically feasible without governance in place to constrain how the technology will actually be used? Now, it's look at a cautionary note with what happened with artificial intelligence, the current boom in AI, which is a huge part of the growth of the US GDP right now. There were all sorts of pious talks talking about how governance in AI was important, and openness, and OpenAI was founded as a nonprofit. But once big profits were perceived in AI, all possibilities of significant governance flew out of the window. There's essentially no effective governance of any kind of AI right now. Solar geoengineering has not burst onto the scene yet, but you've seen the venture capital coming in. And I think the biggest concern is especially with outfits like Stardust starting to appear. Is this what's about to happen with solar geoengineering? Will the profit motive soon outrun any talk about governance? And there has been a lot of so-called research about governance, but it's mostly science fiction. And the best governance in the world won't work if the socio-political system in the world that you're actually stuck with can't implement it, can't make agreements to implement it. So why is there so much revived attention or accelerated attention? And I want to say some of the things that I find, perplexing is that it's not just a few long-standing geoengineering advocates that are pushing this technology and getting involved right now. There are a lot of people with very long-standing diverse portfolios in climate physics that are getting involved, and not only with just theory, but becoming big backers of very expanded research. People like Bjorn Stevens, and people like Jim Hansen, who's come out thinking that we really need to develop solar geoengineering because they think will need to be deployed. So it's this happening in a panic, and I think people are not really thinking through what the use case would actually be for some kind of solar geoengineering, if indeed there is any use case. But the general thing is that even among the scientific community, since we're not making progress on decarbonization, which is the only real solution to halting global warming, we have to do something. And it's true, it's time to panic. But solar geoengineering, I would argue, only makes things worse and puts the Earth climate in a more precarious position. So now, as an academic, it does go against the grain to say that there's some kind of research that shouldn't be done, because there is this natural and to some extent true perception that more information is always better, that we shouldn't give the future the gift of ignorance. So there's this, and it's just research. But the problem is that a lot of the research, as I said, fosters the development of deployable technologies. And the scientists advocating this research may have the best of intentions, and they almost universally say this is not a substitute for decarbonization, but something you do alongside it or afterwards. But once the deployable technology is developed, it won't be the scientists responsible as they are who have a say in who deploys it. It will be venture capital, it will be oligarchs, it will be rogue governments. And if you just think about what Oppenheimer ran into with the Manhattan Project and could not actually, despite sounding the alarm, could not really have any significant effect on nuclear proliferation. So do you trust this kind of technology in the hands of Vladimir Putin or Donald Trump or Elon Musk? That's what the research is doing. That's what a lot of the research is doing. Not so much the simulation research, but the engineering research, which is capturing a lot of the funding right now. And now this is the myth solar geoengineering myth I've been hammering on for a long time, ever since the beginning. There's this, you see this in the newspapers a lot, that solar engineering is just a way to buy time for future decarbonization. And that's completely wrong, because the carbon dioxide is removed only very slowly from the atmosphere over thousands of years, so that any continuing emission accumulates in the atmosphere, leading to ever increasing warming. And the amount of global heating that you are left with at the time that you finally achieve net zero carbon dioxide emissions, that's what you're stuck with for thousands of years. So it's not that you can do some solar geoengineering for the next 100 years, by which time we have gotten to net zero, and then you stop then. No, the accumulated carbon dioxide over that time, you'll be stuck with, barring completely unrealistic an uncertain expansion of air capture, sucking carbon dioxide out of the air. So this is from a 2016 paper I was on with a fairly idealized climate model, which we could run out for 10,000 years easily. For at least the first couple hundred years, 1,000 years or so, this has been borne out in full IPCC type simulations. But in this scenario, this is going to 20,000 years ago, basically Ice Age, and then here's the Holocene where we've been living in pre-industrial times. And then this is the amount, and these curves are these scenarios assuming that we hit net zero at about the time of this square there, and then all CO2 emissions have ceased. And the different curves correspond to different amounts of cumulative carbon emitted as CO2 up to the time that we finally go cold turkey and achieve net zero emissions. It goes up to 5 trillion tons of carbon at the top one. And so you can see that actually over 10,000 years, you do get some recovery of carbon dioxide, but even after 10,000 years, you don't get back to pre-industrial levels. And in fact, it takes well over 100,000 years for silicate weathering to get you back to pre-industrial levels. Worse, if you look at the temperature, because of an interesting cancellation between the rate at which the ocean takes up heat and the rate at which ocean takes up carbon dioxide, sort of time lag, the temperature is fairly flat for thousands of years after you finally stop emitting CO2. It's almost completely flat in the first 1,000 years. And then as the ocean alkalinity is restored, is buffered, and the ocean can take up a little more CO2, it does go down a bit. But basically, we are resetting the climate for 10,000 to 100,000 years, or maybe even more. Now, what happens? So that associated thing with that is the risk of termination shock. This is the figure we used from published work in the 2015 National Research Council report. This is from an idealized climate model. This is from a real coupled ocean-atmosphere climate model. So here, it's a situation where CO2, this is the air temperature versus time, going out to 2100, I think here, and so this dark curve is CO2 is the temperature you get from continued steady emissions of CO2. And then you assume you have continued those steady emissions and then offset it with global warming. You offset it with solar geoengineering to bring down and stabilize the temperature at pre-industrial levels. And then if the solar geoengineering fails because of war or whatever, at this point you very quickly jump up. In this case, 1.5 degrees. And the longer the situation goes on with continued emissions offset by increasing amounts of solar geoengineering, the bigger this termination shock goes. And you get essentially the same sort of thing with slightly different timescales with full coupled ocean atmosphere models. That is the risk that is being faced, and that's because stratospheric aerosols fall out in about 2 years after you stop actively supporting them and deploying them, whereas the carbon dioxide is still sitting there, again, barring some big technological breakthrough and sucking it out. And so this is what I call the problem of millennial commitment. If you need solar geoengineering to keep the temperature from rising to dangerous levels, you're committing future generations to maintaining solar geoengineering essentially forever. Without large-scale carbon dioxide removal, there is no exit strategy. And so solar geoengineering does not buy time for decarbonization. So this just repeats the same thing in a slightly different way. Some people say, okay, and this is in Bill Gates' book, we need solar geoengineering as a plan B in case the world fails to bring CO2 emissions to net zero. And that's exactly the wrong scenario, because in that case, you need to do more and more solar geoengineering every year, as indicated here, under continued CO2 emissions, incurring a bigger and bigger risk of a bigger and bigger magnitude termination shock. So that's exactly the wrong deployment scenario. Again, there is this hope in the solar geoengineering community that, well, we can just do this for a century or so, and then by that time, carbon dioxide removal by industrial processes will bring the CO2 back down to pre-industrial levels. But that would require an undemonstrated scaling up of carbon capture technology by factors of many thousands. In fact, I think we're going to need all the industrial CO2 removal we can get just to achieve net zero after we get industrial emissions of CO2 down by 90% or more. So I think I'm going to skip over this one. because we're running on time. But termination shock is the showstopper, I think. But there are a vast number of additional risks, which I don't have time to go into, and many of them, many additional risks that are probably unknowable in advance. So Tapio Schneider, this had a very interesting paper about the possibility that even if you dim the sun, direct CO2 radiative effects on the surface energy budget can dissipate low clouds. We don't know the threshold for that in the real atmosphere yet, and involves things we don't understand about low clouds. But this is part of this theme that I was mentioning at the beginning, that solar engineering and CO2, if you change the CO2, that affects the top of atmosphere radiation budget in a very different way than it affects the surface radiation budget. So you throw the surface radiation budget way out of kilter, which can affect precipitation, but it also affects this low cloud dissipation. You have unknown global low cloud feedback. There are various things in the distribution of the Earth's albedo that are not well reproduced in most current models. Asymmetric solar geoengineering does clobber sub-Saharan precipitation if it's hemispherically asymmetric. That is a useful thing we have learned from simulations. And then the aerosol effects are different on stratospheric temperature versus the troposphere. Okay. And multiply large unexplored risks from termination shock. In fact, there's been so little research on termination shock, and I think it's an area we need more detailed research, that termination shock figure we used in the 2015 NRC report, that was also used in the Royal Society report that was released last year, late last year, because they couldn't find anything better to use. And there are all sorts of things like rate-induced tipping, meltwater accumulation, ocean stratification, anoxia, the wind effects on the warm ocean currents that can melt Antarctic ice shelves and uncork glaciers, and then compound catastrophes. You know, what if you had a nuclear winter, then nuclear winter-induced famine, and then you hit termination shock because the world wasn't organized to maintain solar geoengineering? That's really a truly existential risk. Okay, so now we're getting to my last few words, and I think some of the increasing comfort level with solar geoengineering and techno-optimism comes from a failure of imagination about what it would be like living under this constant threat of termination shock. So as a spur to imagination, I turned to science fiction, and particularly Star Trek Picard. In season 2, there is a fork in the road where, and at the beginning, when they're going back to an alternate timeline of the year 2400, coming in towards the Earth, there's this grid of climate engineering grid, hexagonal grid. It's obviously not stratospheric aerosol injection. This hexagonal grid, which is maintaining the Earth's climate in the year 2400, and Q, an extra-dimensional being, states humanity had found a way to save the planet they were murdering. He's referring to a change that he made in the 21st century. Humanity had found a way to save the planet they were murdering. And in our case, it's deployment of renewable energy, decarbonization technology. Humanity had found a way to save the planet they were murdering, but in this timeline, they just kept the corpse on life support. And it's actually scientifically plausible, in fact, certain, that if decisions are made in the 21st century that lead to even a century of continued CO2 emissions in 2400, and in fact, well beyond, for 100,000 years later, people will still be living with those consequences. And so that we are at that fork in the road. The reasons for hope. One path we can take is that that's hopeful, is drastic reduction in the cost of renewables, especially photovoltaics. I know Dan doesn't agree with me that this path is feasible, but in 2025, solar and wind passed coal as a global energy source. China emissions are flat or declining for the past 2 years, roughly, because of rapid renewable rollout. And Africa, in fact, leads the world on growth of solar energy. And another case for the technological solvability of decarbonizing is in this wonderful book, Solvable, by Susan Solomon, who studied the energy system very well. But then here's the other fork, the despair. And I think one of the big things that risks the progress that has been made on decarbonization, or the beginnings of the progress that's being made on decarbonization, is rampant fossil fuel energy gluttony by AI data centers. So US data centers are projected to grow to fully 10% of electricity demand just by 2030. And it doesn't stop there. And it's happening in other countries too. And it's driving a huge surge in fossil gas-fired power plants, especially in the United States. And as an example, Meta's Louisiana fossil fuel data center will require a build-out of 3 whole new gas-fired power plants. And there is an alignment of interest between tech oligarchs who don't care what they break, including climate, as long as there's money to be made, and climate repair techno-optimists who think they'll be able to fix whatever the oligarchs break. And as I've said in the funding structure, there's even a sort of a funding route between the techno-optimists in the tech world and the push to develop and deploy solar geoengineering. So this is our path, and I'm almost done. So this is our fork in the road. So there, and again, it's interleaved with artificial intelligence, which has great societal impacts and great potentials on the good and the bad side. So on the good path, we have a renewable energy build out, and there should be a requirement that all the AI data centers supply renewable energy, which had the advantage that renewable energy infrastructure would persist even if the AI bubble breaks, which is quite possible. You have a clean environment, abundant energy without national security risks like what Europe is suffering because of increases in natural gas prices. And you have AI that makes life better for everybody and keep the warming within adaptation limits. There is going to be some warming, and it will be within adaptation limits. But anyone who has struggled with any of the chatbots that have replaced AI chatbots that have replaced customer service knows that AI is allowing people to be fired, but it's not actually fulfilling their role. It's making life worse. It's just a smokescreen, and it's not fulfilling its promise there. But there is a way that targeted AI can fulfill its promise and allow everybody to be more productive and reap the fruits of their own labor, which is not happening now. All the profits are going upwards. And so the other path, the Q continuum path, Earth gets carpeted with data centers. It's a lot like the runaway AI paperclip example of Toby Ord, where AI just decides to reorient everything into making paperclips. Here, AI has already reoriented capital into carpeting the Earth with data centers. That has to be fought. You have unrestricted CO2 emissions, concentration of wealth in the oligarchy. Most people wind up unemployed and impoverished because they have no jobs. But the few that do have jobs are overworked, just like this 996 culture. The planet winds up on life support. There's constant fear of termination shock. And which path will we take? I want to point out, so I've been one of the most vocal people opposing solar geoengineering, but I want to point out that while I've been talking about this more on the anti-side, there are a lot of respected atmospheric scientists, including people like Miles Allen and Julius Slingo, who have signed on to a cautionary petition against deployment of solar geoengineering and against research that could engineering research that could lead to deployment. And I'm not saying everybody should agree with me, but right now the advocates have been speaking out and advocating much more than the people who are signing a cautionary note. A lot of people have the impression it's just me and Mike Mann that have been worried about this, and then there's Naomi Klein, who's not an atmospheric scientist. But among the physics community, people, whether you agree with me or not, there's a need to learn about this because it's coming. To write op-eds, write technical papers, and then speak out. We need a much more vigorous public discussion of this. But if you do agree with me on this, after you have read more about the issues, please do consider signing the petition on solargeoengineering.org. We also have a blog there where we cover things and issues in more detail than we're able to do in the various op-eds we write. And so that's it. Thank you very much.
Thank you, Raymond, for the very informative talk and that threaded so many difficult geopolitical issues in it. I think this is something that everybody should definitely be thinking about and worrying about. So with that, let's open it up for some questions. So we have at least one hand raised. Let me try to find it. Okay,
Yeah,
Alan
it's yeah.
Go ahead.
Yeah.
Okay, thank you. You make a certainly a convincing argument, and not a surprising one, that there is a wrong way to do solar geoengineering. And just as one exemplar, I could bring up a lot of things, but I can't take much of your time. On your transition shock slide, you had an implementation of solar geoengineering that brings us down to pre-industrial and keeps us there for a certain number of years. Now, instead of thinking of geoengineering as even a temporary panacea, we could think of it as sort of an incremental contribution, like many others that have to add up to whatever is going to compensate for the dangers of climate change. So one scenario would be that solar engineering simply brings us down by a half a degree for some number of decades from where we'd have been without it. So it's like with medicine, there's a dosage that's so low that it's ineffective, so high that it kills you. Somewhere in between, perhaps there's a dosage where the benefits exceed the risks.
So that was actually one of the solar geoengineering myths that I skipped over for lack of time, and I'm glad to have a chance to say a little bit about that. So there is this idea that maybe you can do just a little bit of it. There are two ideas. One, that you could do, maybe you just do it for a while and then you gradually, in a controlled way, relax it. So that you don't change how hot the Earth gets, but you change the rate at which you get there. And that assumes that first of all, you are going to control a gradual winding down in an orderly way, and that there's a world that can do that. But it also assumes that there is a world where you can make an agreement to do just, let's say, a half degree worth of solar geoengineering and stop there. But as I've said in one of my articles on this, I can envision a use case for solar geoengineering, but it's a science fiction use case. So if we get all the way to net zero, and the world is so we do decarbonize, we're not emitting CO2 anymore, and the world is maybe a half degree too warm, maybe because of the loss of aerosols from burning dirty coal. We just do a half degree of solar geoengineering and nothing more. But that assumes that we've reached a state where people can make global agreements and stick to them. We can't even reach global agreements anymore on things like nuclear arms control. And so I don't see that. And the timing is all wrong for that scenario, because right now we're still emitting CO2. We haven't even turned the world's CO2 emissions down. So we're talking about introducing a little bit of geoengineering at a time when increased CO2 emissions are just going to wipe out any advantage you get from it. So there'll be inexorable pressure to do more and more of it. So in a very orderly world, I think there would be a use case for, say, just using a little bit of geoengineering as we approach net zero CO2 to make up for the aerosol cooling that we lose by cleaning up dirty fuel emissions, sulfate emissions in the troposphere from dirty fuel. That's actually a pretty cogent use case. I just don't think that we're in the kind of world in the foreseeable future which can actually make an agreement like that.
Yeah, well, I think you have to make heroic assumptions about an orderly world in order to postulate any future path other than as you put it, a train wreck. So,
Well, the thing is, we
so
are
your comment
starting.
is sort of a subset of a broader conundrum here.
Well, the thing is, there are economic forces that are in favor of the renewable energy path, and those forces, if we can just get some politics out of the way, those forces actually do provide some impetus towards a net zero carbon world. And I think if people are in a panic, rather than going in a panic towards something that puts the world in a precarious state like solar geoengineering, we should actually be doing everything we can to bring the CO2 emissions down to the point where, if you believe in solar geoengineering and we actually show that we can make progress on decarbonization, then that's the kind of world where there may be some use case for it. But until we actually start down that path towards declining CO2 emissions globally, we're just not in the kind of world where it's right to release this technology or develop it.
Yeah, I think people's concern is.
Maybe we should. I would like. Are there other questions? I don't want to go on the
Yeah,
same
I'm done.
topic.
All right, it's fine. Let other people
Yeah,
speak.
yeah.
Thank
But
you.
if there are no more, if there aren't any
There are
other
more
questions,
questions from other people, I'm sure.
yeah.
I don't see any raised hands at the moment, but if anybody has a question, they can go ahead and speak up. Okay, here we got one.
Yeah, hey, it's Jonathan Nash here, and I guess I just following on the last. I loved your talk. I guess the question I have for you is like, do you see a way in which we are able to create a respectful forum for discussion? Because it feels to me like as we move forward at these topics that are they're really fiery, right? And I live here in the United States where you know what's going on, and I guess I'd love to hear your impression as to what is needed so that we have productive dialogue. And I think your talk is a good start at that, but I don't know if you have any comments.
Raymond,
Yeah,
before you
actually,
answer that, can I just jump in real quick?
yeah.
Your slides seem to be jumping up and down a little bit. Maybe you can move your scroll a little bit or stop sharing, either one. So,
Oh, yeah. Actually, I'll stop the share. Yeah,
okay,
yeah,
there you go.
yeah. Okay. Yeah, yeah. So how do we actually? Well, first of all, I mean, I still think it's a rather small slice of the public that's even aware of this, and I think maybe it's even still a rather small slice of the physics community that is aware of these issues. And so I'd like to get through to the physics community first, and talks like this are part of it. I think GPC is a good forum for having these kinds of discussions. Maybe I'll even join American Physical Society again, so I can take part in more GPC discussions. So this is a kind of forum. We need to get more informed physics opinions, people thinking about this, but a lot of the issues are also socio-political, and I don't have a lot of faith in, say, political science being able to predict the effect of disruptive technology. So I don't know what to go there. But I do think that these are decisions that have to be made by deliberative democracy. What kind of risks do people want to take on? And what is the right forum for bringing this before the public? I mean, Mike Mann and I write op-eds for The Guardian sometimes, and I write for the Bulletin of Atomic Scientists, which has been very good at covering all sorts of climate things. I reach the Bulletin audience, but it's still a sliver. It's a sliver of people, and I haven't. I would love ideas about how to reach a bigger audience.
Right, because it seems like it's not just you, it's not just one person, right? It has to be, I mean, yeah.
Yeah, I mean, and when I talk about the train wreck, if you ask me what I think our future is going to be, I'm kind of pessimistic. I mean, I'm optimistic that we have the technology to decarbonize and take the good fork. But when I see how slowly decarbonization is happening despite the technological capabilities, I do think that people do stupid things in a panic. And if we continue emitting CO2 and look at the heat stress, which actually Kim Stanley Robinson did a good job of this panic scenario, of outlining this panic scenario. If we look at the heat stress where people can't survive outdoors if the wet bulb temperature is above 40, they die in a matter of hours. Mammals do anyway. But if people start dying during heat waves in Calcutta, we're going to do it. We're going to do it and hope for the best. And I worry about that because this is what we're going to get. And one of the things I communicate to the public, I like to try to communicate to the public, is this is not a technology that has big technological hurdles to deploy. It's something that could be done. And it is what we're going to have. It's the future we are going to have if we don't decarbonize. So maybe this threat is an additional impetus for decarbonization. But people should know that, yeah, maybe we will wind up doing it, but it's going to be a pretty darn awful world, and one that actually does incur true existential risks for humanity.
Thank you so much, Raymond. Raymond has to run off to teach. I'm gonna steal the last 1 minute to just mention something, an initiative by the GPC, just to encourage you guys all to take a look. So we're fundraising for a early career award. It honors Eunice Newton-Foote, who was the first scientist to recognize that the effects of CO2 in infrared radiation. And you can check out the website. We're about $50,000 away from our goal, and we're hoping that this will be the year of climate and that we can support this award fully. And so please check it out and donate if you can. You can also find it on the GPC website. And I think that's important just because, as Raymond said, we need more research, and so we need people doing fundamental research into the effects of solar geoengineering, termination shock, and things like this. I thought it was funny that they used your figure 10 years later since there hadn't been any more research done on it.
Yeah, yeah, no, that was really quite shocking when I was looking over the Royal Society report.
Okay, wonderful. Thank you so much, Raymond, and hopefully we'll see you guys all at the next GPC seminar.
Okay, thank you so much. See you.
Yeah.
Bye.
Thank you.